Hello, my name is Keith Dunnavant, Manager of Data Center Cooling Solutions for Munters in North America. In this video segment, I'll be discussing air-cooled data center design elements. This is a schematic, a very simple schematic of an air-cooled data center that shows all of the parts that are required to manage the air properly in a data center. The first thing you see here circled is the heat rejection component. We are taking return air from contained hot aisle, and we have a supply fan that's pushing it through some form of cooling and ultimately rejecting the heat to the atmosphere, delivering cool air back into the data hall to the servers and repeating the process. So this is the first thing that you need to do, is manage your thermal loads by proper heat rejection. Next, you need to properly remove the particulate that's generated within the data hall. And you can look at this as in a different fashion than most, where you typically have filters in the recirculating cooling units, but that's wasteful. Energy wasteful, because you're filtering air at 50 to sometimes over 100 air changes per hour. If it's all recirculating air, that's not required. You can filter at rates of only 6 to 10 air changes per hour and get plenty of good particulate removal. And by doing that, you can avoid a lot of fan power that you would otherwise waste by excessive filtration. So filtering is the next thing that you need to do. And next we have building pressurization, makeup air introduced into the room, which also is your humidity control component. And so this is going to have both the ability to dehumidify and humidify and filter to a very good degree, usually MERV 13. Of the makeup air that's being introduced into the data hall. Those are your components. Let's drill down now into the heat rejection. We've got a crawl unit shown on the roof that is pulling heat from the contained hot aisle and recirculating back into a supply plenum, flowing through the servers, picking up the heat, and here's your symbol for the heat of the IT equipment that's being introduced. The overall heat may include some lighting and skin loads and electrical equipment. So you want to define your overall heat, your overall room load. And once you know that, you can then use the very common equation, which is mass flow times the specific heat of the air times the temperature difference of the air, the return minus the supply. Usually what you're trying to do with this equation is calculate the proper airflow that is needed to reject the heat properly. So you start out by using the equation to calculate the mass flow, and then you translate that into airflow rates. And we'll talk about that a little bit more in a subsequent series, but you've got your temperature of the return coming back. That's your hot temperature. Often that's 95 Fahrenheit to 100 degrees Fahrenheit. You've got then your supply temperature, which is usually 70 Fahrenheit to 75 Fahrenheit in modern data centers. And then you've got the power necessary to move the air throughout the data center. So you've got a motor driving the fan, and that's consuming power, which is also adding heat in the form of pressurization or doing work on the air. And that additional work has to be, or heat has to be removed from the cooling system. So your total heat of rejection from the system, Q sub R, is equal to the room load, Q, plus whatever amount of power that you're adding to the airstream by your supply fan motors. Fortunately, Munters has an iPhone app to help design engineers make these calculations. You'll learn more about this in a subsequent video segment. But you've got two different modes, a design mode and an analyze mode, which I think you'll find very useful. It is useful to apply a metric of efficiency to your cooling equipment, and the most common metric used by mechanical engineers is the coefficient of performance, which is equal to the kilowatts of heat rejected divided by the power input to the cooling device. So as an example, if your cooling unit is rejecting 250 kilowatts of heat using only 50 kilowatts of power input, then you've got a coefficient of performance of 5. Today in data centers, there's another metric referred to as the power utilization effectiveness, or PUE. In this case, we're going to be looking at the partial PUE, or mechanical PUE, which only accounts for the power consumed by the servers and the power of the cooling equipment. So for partial PUE, you can calculate that from the coefficient of performance, and it's equal to 1 plus 1 divided by the COP. So if your COP is equal to 5, you have a partial PUE of 1.2. If your COP is 10, you have a partial PUE of 1.1. Lower is, of course, better as a PUE. Typical HVAC cooling equipment today has a COP of about 2.5, and this results in a partial PUE of 1.4. More efficient cooling solutions today have partial PUEs less than 1.1. Next, we have to, as part of a overall design strategy, we need to define what the ambient temperatures we're going to use for sizing the cooling equipment. ASHRAE provides guidelines for engineers to use, and this is right out of the ASHRAE Handbook of Fundamentals 2013 edition. We're selecting a city, a sample city, Washington Dulles, Virginia, in the USA for this exercise, and we're going to select the various temperatures to be used for sizing your equipment. So the first thing we're looking at here is the extreme max wet bulb. That's one parameter of interest. We also want to look at the 50-year extreme, both minimum temperatures, which in this case is minus 14.3 Fahrenheit, and maximum 105.2 Fahrenheit. So if you're sizing cooling equipment that is dry bulb driven, such as air-cooled chillers or a air-cooled condensing unit on packaged rooftop equipment, you would usually select as your design temperature the 105.2 to be used. Or if it's on the roof, you may go even higher to 110, 115 to account for additional heat that's being picked up from the roof. If you're designing equipment for that's wet bulb driven, such as evaporative cooling, cooling towers, things of that nature, then you're going to want to be focused more on the maximum wet bulb temperature. In this case, it's 84. If you are designing wet bulb driven processes, then you want to also take a peek at what ASHRAE presents to you in the way of monthly design data. So this is a deeper drill into each month look at the 0.4% design conditions. In this case, we're looking at the monthly wet bulb with the mean coincidental dry bulb temperatures. So we find that in the month of July, we have a wet bulb temperature of 79.8 with a mean coincidental dry bulb of 91.6. Now, why do we want to look at this? Because sometimes you will find that the 0.4% monthly condition is drastically different than the wet bulb extreme. In this case, we are within 4 to 5 degrees of the extreme, which tells us that the extreme max of 84 is realistic and should be used. So our recommended design condition for wet bulb performance-driven equipment would be to use a dry bulb of about 95 to 100 Fahrenheit with the extreme max wet bulb of 84. Here you have for Washington Dulles a psychrometric chart that populates the hour-by-hour weather data in bins. This red bin is 125 to 113 hours, so you'll see that showing up. So these various colors show the frequency of occurrence of ambient conditions for all 8,760 hours of the year. You will see that during a typical year, this is TMY3 data, typical meteorological year, 3rd edition data that's been plotted. But you'll see that typical data does not capture the extreme. So I've plotted here the 100 dry bulb and 84 wet bulb condition, just to show you that you have a nice margin of safety if you use this as your design in relation to what is typically occurring. If you're not familiar with the psychrometric chart, on the x-axis here you have dry bulb temperatures. So this, if you move to the right, you're getting hotter. If you move to the left, you're getting colder. So that's a measure of dry bulb. On the y-axis, vertical axis, is a measure of moisture content. So at the very bottom, there's 0 moisture in the air, and as you move up, there's an increasing amount of moisture in the air. So as you go higher up, you're getting finally to very high moisture contents, and you'll see that that 184 wet is really quite an extreme condition. There are a number of very good resources that you can use for your data center design. ASHRAE has provided some excellent resources from particulate and gaseous contamination in datacom environments, the thermal guidelines, best practices, and design considerations. These are just 4. They have many others. And there's another resource out that just came available late last year, the Data Center Handbook, and Munters is a contributor to this handbook. The Chapter 25 on free cooling, you'll find some additional information on the various ways to accomplish free cooling in a data center. Here we're looking specifically at ASHRAE's recommended thermal guidelines for mission-critical facilities. So just to kind of walk you through this, they have recommended conditions for the air that is supplied to the server. So their recommendation for dry bulb temperature is 64.4 Fahrenheit as the minimum, with a maximum of 80.6. These are the temperatures of the air that are recommended to go right into the inlet of the server. So that's dry bulb temperature. Next, they have recommendations on moisture content, dew point. So as of the even 2013 edition, the recommendation was a minimum dew point of 41.9, and on the high side, a 60% relative humidity with a max dew point of 59. This was recommended. However, there is new research has just come out, and the new recommended low end of relative humidity is going to be reduced this year down to 8% relative humidity. So that's a big change that you'll see going forward. Next, ASHRAE has the allowable limits for the air conditions fed to the servers. Here you see the minimum allowable is 59 Fahrenheit and the maximum is 89.6. This is allowed. You can operate your data center with these conditions. On relative humidity, 20 to 80% is the allowable range. And of course, that's going to be changing down to the 8%. And then you have a maximum dew point of 62.6 allowed for Class A1 servers. This red envelope you see here is the current recommended conditions for the air supplied to the servers. So again, this is plotted on the psychrometric chart. So here you've got the 64.4 and 80.6 at the high end, and your moisture contents up on the y-axis. So this is the current recommended. It will be changing. I've extended this now to show this blue down to the 8% relative humidity. So this is a pretty broad envelope of recommended air conditions to be supplied to servers. And now I've overlaid it with, again, that Washington Dulles TMY3 weather data to show how many hours there are of where the outdoor air condition is just right to fit into this window. And so you'll see that there are quite a number of hours where the outdoor air condition is perfectly within that window, and there are many hours where it's outside of that window. So let's start out with this new change of 8% RH. You might think that perhaps that may not require any more humidification, but you would be incorrect with that assumption. If we take the middle ground of dry bulb temperature of 70 degrees Fahrenheit and match that up to your 8% relative humidity, that's a dew point of about 8.8 in this Dulles environment. And that is going to result in 452 hours a year where the dew point is actually below that. So almost 5% of annual hours where the air outside is too dry, and you will need to add moisture to the data hall to maintain the proper humidity above that 8% minimum. There still is going to be quite a bit of humidification required. Again, this is just for Dulles. It will vary depending on the particular city that you happen to be building your data center in. Next, we're looking at the dew point where you're above the 59 dew point, which is the upper end of recommended. You can see in Washington Dulles there are many hours where the dew point exceeds 59, and it's for the TMY3 data set, it's just over 2,400 hours, which is about 27.5% of the typical annual hours. So a lot of hours where the moisture content of the outside air is too high to be introduced to the data hall. So you would not use this air for an air-cooled in a direct air side economizer condition. You would not want to introduce this because you would be exceeding the humidity levels or dew point levels in your data hall. So drilling down some more into particulate removal, again, this is this element here which has filters. It could have pre-filters, often MERV 8 filters with a MERV 13 filter. It depends on your particular design equipment. I've shown it here as a side stream filter, as a separate component. In actual practice, a more effective way to do it is to install filters on select recirculating cooling units. So here you see a large data center, and these are units on the roof feeding galleries of supply air on both sides. The servers would be running in between here. And we've installed filters on this row of cooling units, and on this row of cooling units, and on this row of cooling units. So if you put filters just on select units in zones, you will get the proper particulate removal. You want to typically make sure that that's on about 20 to 25% of the overall units. And by doing this, you are not putting any burden on all of these other units that don't have any filters. A filter is a resistor. It adds pressure drop. It causes the fan power to increase because you have to pull that air through the filter to remove the particulate. So if you can remove that device, then you remove or shunt fan power and allow your data center to run more energy efficiently. Next, we have the makeup air component. In a data center, you typically want to be introducing about 0.25 to 0.5 air changes per hour of ventilation air into the data hall. And this is for two reasons. One, to maintain proper indoor air quality, because the servers do emit volatile organic compounds. And there's been some research as to what is the minimum, and that's 0.25 air changes per hour to maintain good air quality. In some cases, you may have a building that's not very tight, it's pretty leaky, and you may want to provide some additional up to the 0.5 air changes per hour so that you can maintain good pressurization. So that's the first parameter. By code, it's typically even less than that is what's required to ventilate a data center, but the 0.25 air changes per hour minimum is a good overall recommendation. This makeup air device, if fitted, and it should be, fitted with very good filtration to the MERV 13 level, and it should also have the ability to humidify and to dehumidify. So you will see this dashed line here. Now, that is allowing return air to come back to this unit so that you can use heat from the data center to run over evaporative type humidification media so that you can add moisture to humidify without the need to do any heating. You don't need to boil water in a data center to humidify. There's no reason to waste that power. You've got plenty of heat available in a data center. You might as well use it to put it to good use so that you can humidify essentially for free using that warm air over evaporative medium. Secondly, you want to have dehumidification installed in this device so that during all of those ambient hours where the dew point is well above usually 55 to 59 is the upper end of recommended. So when the outdoor air dew point is high, you want to have the ability to strip out that moisture and drive the dew point of the makeup air down, usually to 48 to 50 dew point, so that you've got a margin of safety to make sure that you're maintaining that data hall well below the upper end of recommended dew point levels. So that's your makeup air system, and Munters has some innovative makeup air designs, both standalone and designs that will integrate with cooling units. So here you see a sample cooling unit that has hot return coming back with optional filters and supply fans and some other components that we'll talk about in another segment. But the makeup air module can append right onto the end here, and it has everything you need to have proper filtration of the makeup air, proper humidification, and proper dehumidification. And when you're able to integrate it in a way like this, you're not introducing another duct penetration into the roof. You can utilize the same power feed for your main cooling unit. So there are many benefits to having an integrated makeup air system. That's it for this video segment. Munters appreciates your attention, and if you'd like to get more information, you can go to our website as shown here. You'll find a wealth of information on data center cooling. Thank you.